Hi everyone. In this video we're going to see how to use the determinant to compute the inverse of a matrix. So let's see how this works by way of an example. So the first step of what we need to do is to compute something called the cofactor matrix, or matrix of cofactors. And it looks like this, where those C's are the cofactors of the corresponding entries. And we saw how to compute those when we were doing cofactor expansion. I think it's useful to have kind of a running example to compare this to. So let's do an example over here with the matrix A equal to this. And to compute the cofactors, we need to do the following. For C11, remember the cofactor is what we get when we cross out the column and the row that the indices indicate and then compute the determinant of what's left. So for 1, 2, I would cancel out the first row and second column. So the determinant I need to compute is 0, minus 2, 2, 2. And that determinant is 4. But remember that we're looking here for the cofactors, not just the minors, which is the determinant of that submatrix. So we have to keep in mind that there is this checkerboard of pluses and minuses. And for that 1, 2 entry, that's going to be a negative. So we're going to have a negative 4 here. We'll take the negative of that determinant. And then in the 1, 3 slot, we're back to positive. So we can take the determinant of that submatrix. So that'll be minus 2. And then we just got to keep doing this. And I think that maybe I'll just write them all down right now. So you can compute the determinants of the rest of the cofactors and make sure you're getting what I'm getting. Make sure to use that checkerboard of pluses and minuses, because you do have to negate some of the minors when you're working this out. Okay, so that's step 1. We compute the cofactor matrix. The next step is to take the transpose of that matrix, and that will give us something called the adjoint. And you probably read in the text we haven't had cause to use it yet, but the transpose of a matrix is just what you get when you flip it along its diagonal. In the notation that I use, I would write this like this. The adjoint of A is equal to the cofactor matrix of A transpose. So we'd use that superscript capital T to indicate we're taking the transpose of the matrix. So now for our example, we're going to take the transpose of this matrix to get the adjoint for A. So that means that every column will become a row, and every row will become a column. And again, this is exactly what you would get if you just reflected the entries in the matrix across the line that goes along the diagonal, except the numbers wouldn't be upside down. All right, so once we have the adjoint, then the next step is where the magic really comes in. So here is our fairy dust. It turns out that if you multiply a matrix by its adjoint, the product of those two things will be a matrix that's 0 everywhere except on the diagonal, and on the diagonal it has always the value determinant A. So let me write that down. So if I take the adjoint of a matrix and I multiply it by the matrix, or if I do it the other way around, if I do A times the adjoint of A, I'm going to get a matrix that looks like this. And so on, all the way down the diagonal. So whatever that value is, it's going to be along the diagonal, and everything else will be 0. So if A times the adjoint of A is equal to this matrix, which I think I'll write a little bit more compactly as this. So this is just the determinant of A times the identity matrix. Right? As a scalar multiple, that'll just give us the matrix that we just were looking at with the determinant A values along the diagonal. All right, so if this is to be believed, then this means that if I multiply, say, both sides of this expression by 1 over the determinant of A, then I will get basically a formula for the inverse. Because A times this matrix is equal to the identity matrix. And that means that that's the inverse of A. That's our last step. Now the determinant of this matrix, I'm going to go ahead and give away. It's -6. So if I want to compute the actual inverse itself, I'll take 1 over -6, or -1/6, and multiply the adjoint matrix by that scalar. And now maybe you can see why I was hinting about how you kind of always end up with fractions in the procedure that you go through in computing the inverse of a matrix. Right? You see we are multiplying by 1 over the determinant here. Okay, so that is how you compute the inverse of a matrix by using determinants, and you may be asking, why on earth would you want to do this? Well, just imagine you're going to compute the determinant of the matrix anyway, and I know this is a 3x3, so you could have used that other method for computing the determinant where you add those two columns and just, it's called the rule of Saros. But if you were working with a much bigger matrix, you would end up finding all of these cofactors anyway, just in your computation of the determinant. So if you've got all that stuff already computed, you may as well just use it to compute the inverse if you've got it all done already. However, if you don't need the determinant of your matrix, Gauss-Jordan is probably the best way to go. Okay, so that's it for this video and this short part of the module. Up next is Cramer's rule.